continued on the topic of period and started to look at the concept of waves. The question that I left you with yesterday, if each one of these time periods is 1 second, which of those pictures would have the highest frequency?
C. Because it's not a normal wave in the second.
So this one has 1, 2.5 in 1 second. Which one has the shortest period?
D. Because it has the least amount of waves in the frequency. The cycle.
What's the difference between
Frequency is how many there is.
how many there is in 1 second? So that's complete waves. How this is different than period.
Hold on. Don't say nothing.
It's always the opposite.
Time required for vibrating object to complete a cycle.
9 seconds. It takes for 1 wave to go by.
So for C, it would be 0.25 seconds for 1 wave.
So 1 second is 2.5 waves. So this period is going to be 4 seconds per 1 cycle. So 0.4 seconds per 1 cycle. Okay, what's going to be?
33.3. Actually, I did pretty good
How many waves, complete waves, do you have here? How many complete waves do you have here?
1.5.
1.5. Okay. So that means that in 1 second, you have 1.5 waves, but that is a frequency. Okay. You need to convert this. So 1 divided by 1.5 is?
Everybody meeting is late today for to like it. 0.7. I think
The whole school is doing it.
So the period of this is 0.7 seconds for 1 cycle to happen.
Did the walk.
Picture B. How many complete waves do we have? 1. So that means that in 1 second, we have 1 cycle. Picture B. How many complete waves do we have? How many complete waves do we have? Complete wave. You need to know what a complete cycle is. So in 1 second, you have 0.5 waves happening. So how much time is it going to take for one cycle?
Pardon?
How much time is it going to take for one complete cycle?
2 seconds.
So this is 2 seconds for one cycle. Therefore, which of these has the longest period? D has the longest. C has the shortest frequency. G has the longest period. Do you remember what wavelength is?
Wavelength? It's the distance between the waves.
Between a crust.
Okay.
Yeah.
So we can either choose the point between two crests or two troughs, and this is the wavelength. So you said that C had the shortest frequency because it had lots of waves in a 1 second.
Good morning, everyone. If I could please have your attention for the morning announcement.
So you said picture C had the shortest frequency. Because it has the shortest frequency, what is the wavelength like compared to the other pictures? Compare the frequency and the wavelength.
Also celebrating a birthday today, this June 7th. It's Miss Guliak, so happy birthday.
Picture should see has the shortest wavelength because it has the highest frequency. As you decrease the wavelength, you increase the frequency. If the wavelength is very, very long, you're not going to have as many waves in one period of time. Okay, wavelength and period. You said that picture D had the longest wavelength. It also has the longest period. So if you have a great distance between two waves, it's going to take a lot longer to go through one complete wave. So when you increase your wavelength, you increase how long it's going to take for one wave or one cycle to happen. The period of wave D is 2 seconds in order for one complete wave to happen.
Pardon?
Pardon?
What did you
Picture D
Yeah.
takes 2 seconds for one complete wave to happen.
Yeah.
That means in 1 second, you only get half a wave. What is the relationship between period and frequency?
A shorter period equals a higher frequency.
Mm-hmm. The less amount of time it takes to make one complete wave, the more waves you're going to have in a time period. So, short period, more waves. Longer period of time to go through that complete cycle, that means that you're going to have less waves per second.
With a higher frequency, would the waves be less powerful?
No, high frequency would be more powerful. Think about if you're standing on a beach and you have a lot of waves hitting the beach in one minute. But those waves have a lot of energy. Versus if you only have maybe one wave per minute, a lot less energy is being transmitted to that beach. For example, gamma radiation has a very high frequency. Extremely dangerous to us in low dose or even low doses, unless it's being specifically targeted for cancer treatments, versus something that has a low frequency would be radio waves. We use radio waves all the time. Mind you, really anything at a high dose can be harmful. Even something like water. We can actually consume too much water. Alright, I wasn't able to get the wave generator for today. So we'll have to work through this as a paper problem for now, and hopefully I can get the wave generator over to Sturgis. Let me share generator because it's a very pricey piece of equipment. Alright, so literally, a wave table is something that sits on 4 legs. And you have a light bulb underneath so that it shines through the water and you see the pattern on the ceiling. And what happens is you stick the wave generator in one side and it sends waves through the water. And you can see the bands of the waves on the ceiling and start counting the number of waves in a second. So that's what this problem is talking about. And like I said, hopefully I can get it over here today or next week. So it says, oh wait, sorry, we're going to do some teaching first. I haven't learned this new formula. So let's learn the formula before I start giving you questions. Alright, so transverse wave. Transverse means across. So you can have a standing wave like this. Or remember, if you have something that's going back and forth and oscillating pendulum, that we would just take this wave and put it down horizontally, and you would be able to see that wave on a piece of paper. So, just stop this. I'm missing the slide again. The second type of wave that we talked about is a longitudinal wave. So do you remember when we had the spring on the table and we drew some springs back so that the wave actually transferred down along the length? This is another example of a wave. Do you know how sound waves work? It's actually not a transverse wave. Let me see here.
Concept of waves involves basic definitions. We're going to look at a FET simulation and examine period and frequency using a speaker. Now when I turn on the speaker without turning on the sound, you can see that the speaker moves in and out. And basically what a speaker is doing is disturbing the air in front of it, creating compressed air, and then as it pulls back, creating expanded air as it makes a vacuum. The expanded air is known as rarefacted air. So as it's pushing forward, it creates a compression wave, which is indicated by the white lines on the diagram, and as it pulls back, it creates a rarefacted wave, indicated by the dark lines in the diagram. Now, those differences in pressure are going to be detected by your eardrum, And then that's what your brain is going to sense as various frequencies as your eardrum vibrates at the same rate that the speaker is moving in and out. Now we also see that the speaker is disturbing the air horizontally. It's disturbing it left to right as it creates the expanded and compressed regions of air. And because it's disturbing it in the same direction that the air is actually traveling, we can see that the air is actually traveling in a circular path, but horizontally towards my ear. Because the disturbance is in the same direction, we say that's a longitudinal wave. Now we want to examine something called frequency. And if I just look at my simulation, we can see that it's making about 1 wave per second. So a fairly low frequency wave. 1 wave per second is hitting my eardrum, and we would say that has a frequency of 1 hertz.
Sound transmits differently based on temperature. Have you ever noticed that you can hear the traffic going through town a lot better at -40 than you can on a day like this? There's quite a difference. So this is an example of a longitudinal wave where the bands are trying to show you where the molecules are close together versus where they are not. How would you figure out a wavelength for this? Or a wave. How would you figure out a wave for this? Because it's not your standard up, down, transverse wave.
How many there are?
Where it's more condensed, it would be higher.
Pardon?
Where it's more condensed, it would be higher.
So that wave, it would be like between each, there would be like 3 blue, and then there'd be like 1, 2, 3, 4, 5, 6 red.
Yep.
You would count how many there is in the red and then how many there is in the blue to find a distance between them.
So would a wave go from here to here then?
Yeah.
That's what. Remember, it's going to go back to its resting point. So if you choose that first bar on the left-hand side as your resting point, where is the next resting point?
On the other.
Right there. And so that's actually would be considered a full cycle, because the speaker would go out, compress the air, and then come back in, and you would have space. Then the next cycle would be another compression, and then another relaxation. One time we found an old set of speakers and we hooked them up to Devin Barabash's sound system in the car and cranked the bass, and then we poured paint in the speakers and took pictures of the paint jumping with the different songs. Very interesting. Alright, so you saw a relationship between the wavelength and the frequency. We can manipulate that relationship in order to figure out how fast that wave is moving. Because we know that it's a short wavelength. That wave is moving fast. How fast is fast? So we have a new formula. V is speed. Hopefully that's something that you remember a little bit from working with your physics unit last year in Science 10 equals distance divided by time. I know we can adapt that to waves because time is how fast it's going, which is your period. Distance is the wavelength. is the chart that we created. Or we're doing something with the data, which means we don't have the original data in the computer. What we want to do is create a sheet that has all of the original data.
Okay.
And then do all the things on it.
Okay. I'll pull data.
If you use your yellow book, like what you were recording in your yellow book is really good because you have the plot number and then the different measurements.
Okay.
You need to do the same thing today. But that's what we should have for raw data. And I'll have to change the measures because I think I put centimeters at the top of that chart.
Yep.
Yeah.
I'm just going to because I have my software. So I'm just doing this for code days.
So if you want to switch to the other one, even if you just put plot number and then the measurements, we can fill in the rest of it.
Okay.
So let's say we have a waterway, and there is 13.5 meters between the crest and the trough. The water goes up and down 15 times in 24.0 seconds. We want to know how fast that wave is going. My suggestion for you when working with wave questions is to draw it out. You need to be able to take all of this information in and make sense of it. That is skill. It's an amazing skill to have. If you can look through a physics problem and actually visualize it, wow. So let's draw a wave. Is 13.5 meters our wavelength? No, it's not. How do you know, Matthew?
Said between the crest and the trough.
Yes, which means it's from here to here is 13.5 meters. Which means from this crest to this trough is going to be 13.5 meters. But wavelength, you need to know crest to crest. How are you going to figure out the wavelength? Between one crest and another crest.
Measure. So you just add up the 13 point.
Adding it together. 13.5 plus 13.5. Wavelength
27 meters.
is 27.0 meters. You have to make sure that you keep track of your significant digits here. It tells you that the water goes up and down 15 times in 24 seconds. Why is that information important?
Because then you can get the time of one.
Exactly the count. Okay. And if you're going to get the time for one, you can use the frequency calculation. You could use the period calculation. I'm going to suggest the frequency calculation because then we can go right to this formula when we're done. So we're told that we have an up-down motion. Is that a full cycle?
No.
So if we go up and down, is that one full cycle of a wave?
No.
Yes, it is. Okay. So F is equal to the number of cycles divided by the time. We're told that we're going up and down 15 times, that's 15 cycles, in 24.0 seconds. You should be able to calculate how many waves you will get in 1 second.
What's H again? What's H? Don't say height.
Distance between the crests of the waves.
How many waves are we going to get in 1 second?
5 eighths.
6.25.
0.6. You only get 2 significant figures. So you do not actually get a complete wave in 1 second. But the question is asking for how fast is that wave coming in? Do you want to use this one, or do you want to use this one? Calculate how fast that wave is
Bottom.
bottom one. If you want, I can show you how to calculate this one. It is 2 steps as well, so you're not going to save any time doing the second one. So the speed of a wave is how long that wave it is, and how many waves you're getting in a second. The distance between 2 crests is 27.0 meters, and you have 0.63 waves every second. If you multiply those two numbers together, you'll calculate how fast that wave is actually moving. How fast is that wave moving?
17 meters.
That wave is moving 17 meters per second. You only get 2 significant figures for this calculation. It is possible to use E equals V over 2. It's still 2 steps though. Put myself another slide. Alright, so just going to draw this wave again. We've already figured out that from crest to crest is going to be 27.0 meters as a wavelength. It is possible to use V equals D over T to solve this. How would you figure out how far those waves are moving? Each wave has a wavelength of 27.0 meters. And the wave goes up and down 15 times.
You take 27 multiplied by 15.
Yep, you do. So that will give you how far that wave moves.
405 meters.
Mm-hmm.
So V.
So 27.0 meters times 15 cycles. And that wave sequence is going to move the water 405 meters. What is the time period? What is the time period for the 15 waves?
24 seconds.
24 seconds. So V equals distance divided by time. Your distance that your waves have moved is 405 meters. Your time is 24.0 seconds.
It's just another way to do it.
Do the calculation, do it exactly the same number. That's the first step. What I want to show you with this is that with some of these questions, a lot of this there is more than one way to work through this. So please, if you think there's another way, try it out. See if it works. If it doesn't work, we'll work through it together and find out why it doesn't work. There's all sorts of ways to think through a math problem. Alright, light travels. About the parts of the way. Really fascinating things to start taking a look at. We know the speed of light. It's 3 times 10 to the 8 meters per second. Well, I would think it would be pretty awesome if our vehicles drove at the speed of light. Being regimentally plus 1 second. Definitely would not be opening up your window to let anyone fresh air.
Why?
You're kind of like you put it out the window 100 kilometers an hour.
Oh.
Can you imagine going at the speed of light and falling out of it?
What's the speed of sound? Why do that?
Is sound faster or slower?
Slow. Because you can break the sounds of your planes.
Yes, you can. Have you ever left a cross the field and seen your smoking? Person swings the bat, hits the ball, they're running, and then all of a sudden you hear the person hitting the ball. I cannot remember what the number is, but it is slower than the speed of light. The wavelength of light is 450 nanometers. What you're being asked to do is to calculate the frequency. So how many light waves are you getting per second?
Whoa, 340 meters per second.
Meters per second.
That's what I said, meters. 340 meters per second. 140 seconds.
So if we say that light has a or travels at 3.00 times 10 to the 8 meters per second. Is that a wavelength? Is that a speed? Is that a period? Is that a frequency? What is it?
That's
Meters per second.
Meters per second. What is it?
Speed, V.
Feet.
Oh!
All right. 450 nanometers. 450 nanometers. What is that? Is it a period? Is it a frequency? Is it well, it tells you a couple of words before what it is. If the wavelength of light is 450 nanometers.
That's the.
What's wavelength? Without even doing the math, can you spot an issue that we're going to have? Can you spot the issue?
How big is a nanometer?
Yes. How many is an nanometer?
Did I do that?
How many nanometers are in a meter? Oh, metric review. Metric review alert. Okay. So we have a base unit here. If we go this way, we get to millimeters.
Thank you.
What's after millimeters?
Centimeters.
Oh, sorry, this is centimeters. And this would be millimeters. What comes after that?
Nanomillimeters.
Kilometers is like.
Nano. Nanometer.
is there
Oh, wow. I think we need to get a metric map of that you can put down on your tables.
Centimeters.
Okay, get out your blue tables, please. You are going to do a metric map.
Secretly.
The problem that we have with using the wavelength of light is that it is incredibly small, and we will need to do a unit conversion to do this. There is 1.0 times 10 to the 9 nanometers in 1 meter. You need to convert 450. We want to get to meters. We have nanometers. There is 1.0 times 10 to the 9 nanometers in 1 meter. Please calculate the wavelength so that it is in meters.
I did. I heard stole that.
Well, if you're dividing by an exponent,
450. Oh, maybe small factors.
Multiply by the reciprocal.
yeah.
1 second, I gotta count the amount of
Zeros.
You would not multiply by this.
4.5 times 7.
Well, not really.
So that is equal to 4.7 times 10 to the negative 7 meters. It is a lot easier to try to convert the meters in the wavelength question than to try to change the meters in the speed calculation, which I need to put my units back into speed. All right, the next step, you're being asked to calculate what is the frequency. Which formula are you going to use to calculate your frequency?
First one.
The last one?
The first one on the bottom. I knew that.
V equals the wavelength times the frequency. We are solving for the frequency. If we are solving for F, what you might want to do is rearrange your question. However, if you don't, that's fine. I would personally do this, so that I know if I divide each side by wavelength divided by wavelength is 1. So my formula for calculating frequency is velocity divided by the wavelength.
Ooh.
You could put in the numbers for the original calculation and just solve for that. It should lead you to the same destination. The speed of light is 3.00 times 10 exponent 8 meters per second. Your wavelength is 4.5 times 10 to the negative 7 meters. Meters divided by meters is equal to 1. Try this calculation.
So, Ms. Patterson, it'd be just 2 sig figs then?
For this question, there will be 2 sig figs.
Miss Patterson, F equals B over, is that wavelength? Is that wavelength V divided by?
Wavelength, yes. You should get an answer of 6.7 times 10 exponent 14. The biggest challenge with these 3 formulas is applying them to a context and figuring out what is the particular question I'm asking you to do. We're going to go back to the worksheet that you received yesterday, which is the one with all the pictures on the front. Starting on picture number 8, or question number 8. We're going to continue working through this worksheet tomorrow. Tomorrow is going to be a practice day.